So our next speaker is Dr. Bill Kim. Bill received his PhD in inorganic chemistry from the University of Tennessee in 1996 and subsequently worked as a postdoc research associate at Vanderbilt. He began his career at the Seven River National Lab in 1998 and is currently working within the Chemical Processing Technology Group in the Environmental Stewardship Directorate. Bill has experience in inorganic synthesis, material science, and chemical process development. His research assignments have included numerous projects associated with Hanford Waste Treatment Plant, flow sheets development, and supporting SRS operations through testing to support high-level waste characterization, ion exchange processing, and high-level waste tank cleaning and closure. The current presentation is focused on testing conducted to support SRS tank closure activities.
Okay, I know a lot of the talks today have been focused on modeling with a little bit of experimental. This talk will be pretty much entirely experimental testing that we have done supporting closure. We've evaluated really for the first time the release of radionuclides from closed waste tanks using actual waste samples. We looked at 2 different samples over the course of the last, say, 3 or 4 years. So I'll show you how we did that and show you some of the results from that. A little bit of background here. I suspect most of you are familiar with all of this. I'll go through it quickly, but you know we have 51 underground tanks at SRS. They contain high-level waste from dissolved reactor targets that were dissolved in nitric acid. We extracted uranium and plutonium. We neutralized that material, and the waste in the tanks contains fission products, target materials, processed chemicals from various sources. In the end, we have in the tanks insoluble metal oxides that we call sludge. We have an aqueous phase that we call supernate, and we concentrate that material routinely through evaporation, and that causes precipitation of insoluble salts that we call salt cake. When you get to the point of closing a high-level waste tank, for the most part, you removed all of that material except for the sludge, the insoluble sludge materials. Current practice for closing the tanks, you've probably all heard this legal term, is the removal of the material to the maximum extent practical. We use mechanical sluicing and in some cases chemical cleaning. But there is always a sludge heel that remains. You then disconnect the transfer lines and fill the internal volume with grout. We have closed 8 waste tanks to date, some in F tank farm and some in H, as indicated by the letters there. And as you all know, we've done performance assessment modeling of the release of those radionuclides from the closed tanks. It is based, the PA modeling is based primarily on published solubility data for assumed metal species. Not a lot of actual data from tank materials and evaluations of their solubility. We use natural infiltrating groundwater and expose it to a grout-filled material that contains residual waste solids. That's sort of the model for how we look at this system. We're looking at uranium, neptunium, plutonium, technetium, and iodine in our testing because those are the most likely contamination risk drivers. So a little cartoon of the system that we're modeling. You have infiltrating water, which is SRS groundwater, coming into the top of a tank that has grout on the top and a residual waste layer on the bottom, and out of the bottom of that and possibly the sides of that tank comes radionuclide-bearing porewater fluid. So the question is, what's the solubility of those radionuclides under those conditions? Based on the various modeling efforts that were done, target conditions for testing were developed. We're trying to mimic thousands of years of aging of the waste tank. So we have to estimate what the conditions will be. So they developed these targets, and my goal was to see if I could produce these targets and then evaluate the solubility of the materials under those conditions. So there were really 3 target conditions, and they're really listed in order here. The reducing region 2 is soon after you've closed the tank. The grout is reducing. It produces a reducing environment, and the pH is still relatively high, either from the residual waste or the grout-filled material itself. So initially, you have reducing conditions. That's EH, it's oxidation reduction potential for the system, and a relatively high pH. As the tank ages, you become oxidizing. A big swing in EH during that period is assumed. The pH remains high, and then eventually the tank becomes a little more oxidizing and the pH begins to drop. So those are the conditions that I was concerned about the solubility of the radionuclides in the heel materials of the tanks, and that was the focus of the testing. This just shows you over time as many volumes of pore fluid go through the system, shows you the trends predicted for pH, you see that drop, and the trends predicted for EH, you see it increase stepwise. This is all based on assumed chemical species and equilibrium conditions. So this is a photograph of 2 of our tanks. These are the 2 tanks that we tested. Tank 18 is shown here, and tank 12 here. This is after most of the waste was removed and prior to closure. And you can see the residual materials on the floors. Obviously, these 2 tanks look very different. Tank 18 is what we call a type 4 tank. Holds a little over 1 million gallons. There are very few obstructions. The waste in this particular tank was not typical of Purex HM type waste. We had about 1,000 gallons left in this tank. It's currently filled with grout, and the testing that we did for radionuclide release from materials removed from that floor is referenced here. Tank 12 looks very different, a little less than 1 million gallons, has a lot of obstructions. The waste is more typical, Purex HM Thorax. The waste removal included both mechanical and chemical cleaning. Now, chemical cleaning in this case included aluminum dissolution using caustic, which the introduction of caustics is not really a new chemical to the system, followed by oxalic acid cleaning. And the addition of oxalate has the potential to really change the chemistry. So there was interest in looking at this tank in particular. They did a good job of removing waste, about 1,000 gallons left. It also is filled with grout, and this is the report that we've just issued focused on the testing we did looking at the release of the radionuclides. So when we sample these tanks, it's done very carefully with mapping of the tank floor, documentation of where individual samples came from, and you can see we got a host of samples, and each one of those we know exactly where it came from. Multiple floor samples collected and analyzed. That's the characterization report for those samples. We selected this particular sample for leach testing because it tended to have the highest concentrations of the radionuclides that we cared about. Same thing for tank 12. Tank 12, because of the obstructions, there was a mound of material that potentially might not have even been highly disturbed that was left in the tank, as well as routine floor samples that were collected. So all of the characterization samples and the samples that we tested for solubility were blends of the mound and the floor samples. Quickly show you some characterization data. Both of the tanks are dominated by iron and aluminum, but the other components vary considerably between them. Uranium was one of the next of the high primary waste components for tank 18, but mercury, there was a lot of mercury in tank 12. So if you compare the two, tank 12 bulk composition was high in mercury and thorium and low in uranium versus tank 18. If you look at the radionuclides, tank 12 had less technetium, less of some of the plutonium isotopes, more iodine, and more Pu-238 in the tank 12. And the iodine in particular, I'm referring to tank 12 in that parentheses, was quite a bit higher than we expected for tank 12. So there was a lot of interest in knowing how that iodine, and you saw in some of the earlier presentations that iodine is a driver for us in the PA world. There was a lot of interest in what was the solubility of the iodine. And then they were comparable with regard to neptunium and another of the plutonium isotopes. So just to give you a little background on how we have to test these materials, this is our our shielded cells facility in the lab. All the testing has to be done remotely with manipulators that give you this motion. So we had to design equipment that we could complete the testing with those limitations. So it was remote sample handling with manipulators, gases and probes that were needed introduced into the front wall penetrations in that facility. That facility has a pretty big swing in temperature through the season, so we needed temperature control. These were the things we had to think about as we designed the tests. So through a series of tests that were done initially with simulants, we came up with a method to test and try to reach those target conditions that I showed you in some of the early slides. And in the end, it ended up being a 3-component sample that we made for each condition of interest. The first component is a grout pore water simulant that's composed of infiltrating water. It's a simulant of SRS groundwater of that composition, plus calcium carbonate added to saturation and calcium hydroxide utilized to adjust the pH as needed. So that's the first component. Second component was either a grout using the same recipe used for whichever tank we were interested in, or a simplified grout representative phase, such as calcium carbonate. We discovered early on in the testing that approaching the pH and EH targets that we had been given was difficult under oxidizing conditions when you utilize grout. Under the oxidizing conditions, the grout has greatly changed. It's aged over many years and had many volumes of liquid pass through it. So we simplified the grout phase to just calcium carbonate, a phase that we thought would persist and a phase that was impacting the pH. We also, for the reducing cases, added ferrous sulfide to get the oxidation reduction potential down in the range or near the range that we were targeting. The third phase was the actual tank waste solids, either tank 12 or tank 18. We typically, although not in all cases, washed those solids with groundwater simulants because you can imagine over time the materials in the tanks are more washed than not washed. So those are the components of the simulants. We then had to control the atmosphere to produce the oxidation reduction potentials that we were targeting. For the oxidizing samples, we purged with air, typically stripped of CO2 because CO2 will affect the pH. And for the reducing samples, we purged with nitrogen. So I don't know how well you can see these pictures, but that's a picture of the equipment. In order to control the atmospheres in the sample, we needed a series of vessels to either strip out CO2 or humidify the gas so that we didn't continually lose sample due to evaporation. So it ended up being a fairly complicated piece of equipment to operate in the cells. But bottom line, each sample sits over a stir plate. We stirred the samples with magnetic stir bars. We used a water bath bath recirculator that's not shown to control the temperature, to deal with the temperature swings in the facility. And then we use customized glass leach test and gas treatment vessels, which are shown over here. That's an example of a caustic scrubber where we're just bubbling our air through 5 molar sodium hydroxide to strip out the CO2. And this is a humidifier vessel that either isolated the caustic scrubber from the actual sample or was used to, as I said, saturate the gas flow such to minimize evaporation from the actual sample. Okay, won't go through this, but the actual samples are the OR3, OR2, RR2 samples, and all these other vessels are to produce that atmosphere within the test vessel that we want. For oxidizing samples, it would go through a caustic scrubber, then a humidifier, and then through the leach vessel. Another issue in the facility is this facility is many decades old. It's had lots of different types of samples come through. Contamination is an issue, and the concentrations we expected to see were very near our detection limits analytically. So it was a challenge to analyze these samples and avoid contamination and prove to ourselves that we did not have contamination. So substantial background, especially for plutonium. So this is what we did. We used syringes with a filter on the end. We would pull a sample out of those vessels, put it directly in a syringe, attach this to a sample bottle with these quick connects, so that once this is filtered, it goes directly into a sample bottle that is vented with a filter on the downstream side, because plutonium has the characteristic that it will almost crawl over every surface inside that cell. So we had to really isolate it on both sides, upstream and downstream. Let's see. Isolated the samples immediately after filtration, so we never opened the bottles in the cells. We cleaned the cell floor. We cleaned the outsides of the bottles once they went to analytical, and were careful not to contaminate it once we got it there. And we analyzed control samples to convince ourselves that contamination was not an issue. And for the most part, almost exclusively, contamination was eliminated. So that's the equipment in the cells with actual samples inside the test vessels. Oxidizing samples were washed. Reducing samples were tested either washed or unwashed. Remember, the reducing was the beginning part of the aging process that we were interested in, so we looked at both. Collected samples weekly and continued for about 2 months. So we collected 8 to 10 samples to confirm we had reached an equilibrium and that we believe we had concentrations that were representative of the solubility limits for the radionuclides. We monitored the pH and the EH weekly, really continually, and we had to make adjustments in many cases to maintain those targets, or at least approach those targets. As is the case with all new forms of testing, you have issues and observations. In general, our subsampling system worked well, minimized contamination. We were able to reach our target pH values, although for one of the samples, it really consumed base equivalents. We were continually having to add calcium hydroxide to keep the pH up, probably due to dissolution of some metals within the sample. Target EH values could not be achieved. I don't have them side by side, but the reducing potential target was really low, like negative 450. And I think the lowest we reached was negative 200. But those targets were based on a lot of assumptions, and you really don't know until you actually try to do it in the lab how low you can go or how high in EH potential. But we didn't achieve the targets, but we did achieve ranges in oxidation reduction potential from 0.5 to 0.7 volts, which is a pretty decent range for these samples. For tank 18, we once had a siphon-induced backflow of water from our water bath into one of our samples. Modified our test equipment based on that. For tank 18, we also saw during our wash for oxidizing samples, we actually lost most of our uranium and later figured out that the uranium during the interim period between the tank being emptied and the tank being closed, it was exposed to air, and the uranium reacted with CO2 in the air and converted to a uranium phase that really is not typical of our waste, and was quite soluble. So I'll show you in a minute. For that reason, some of the uranium data on tank 18 is, may not represent solubility depending on what solubility you're talking about. So we learned things, as is the point, as we went along. Tank 12, we had an issue with agitating the samples. Still don't understand it. We couldn't stir the samples. They were not that thick. It was unusual. So probably in the future we'll evaluate that ahead of time to see if our agitation method is going to work. Because of that, we did manual agitation. You have to be flexible when you're working in the cells, and you have your equipment in there. You've got to do your best to make it work. So we did manual agitation daily because we were testing for weeks and weeks and weeks. I don't know that it had a big impact. It may have caused our next problem, which was one of our vessels ruptured in the middle of testing. So we may evaluate our vessel design in future testing. Iodine leaching levels for tank 12 were right at detection or just below. And the more sample size, more sample volume you can give them, the longer counting times they use, the lower detection they can go. But we were pretty low, down in single-digit DPM per mil. But in the future, we may try to design the test a little differently to get them more volume. So here are some results. There's a lot of numbers. I won't go through all of them. The things you want to notice is that these are the EH range that we achieved was about negative 200 to positive 500 for tank 18. That's the 0.7 volt range I referred to. pH targets we generally reached. Concentrations of the radionuclides on a molar basis in general are really low. E to the negative 10th, E to the negative 9th, or even 11th. Uranium was the most soluble radionuclide. These are concentrations even after losing most of the uranium to the wash. Uranium came out much more easily than the other radionuclides. We had some other issues. Technetium data trends for tank 18 indicated that even in 2 months we might not have reached equilibrium. Tank 12 results are shown on the bottom. We did not reach the same range of EH for these samples. We did drive the samples to near the pH targets that we were trying to, but as I said, we struggled to maintain them there continually. So in general, technetium and neptunium solubility is comparable for tank 18 and tank 12. Uranium and plutonium solubility was lower for tank 12 than tank 18. They were happy to see that, the folks in closure. Iodine solubility is generally below or near detectable analytical limits. So we're getting data. You'll see on the next slide, they had made a lot of, I'll say, conservative assumptions about solubility for the performance assessments. This data could now be compared to that and perhaps be implemented in future performance assessments revisions. This is an example of some of the predicted plutonium and uranium residual waste solubilities that were utilized in the performance assessments. In general, they tended to use the high values, and I won't go all through this table, but I'll just tell you that they kind of looked at 3 cases. One where you're assuming a phase, and you're assuming that for the oxidizing cases, you're assuming that the sample is in equilibrium with dissolved oxygen. Well, that's not necessarily a case that you can achieve readily. There's kinetic limitations on that. So they also looked at cases where you did not have equilibrium with dissolved oxygen. And then they looked at cases where rather than having a pure phase, you had a coprecipitate phase. You saw from the compositions, this is mostly iron and aluminum and other species. There's always been a question, how do the metals exist? Are they individual particles, plutonium, uranium, or are they coprecipitated within this other matrix? So they also looked at coprecipitated phases where the solubility of the radionuclide was based on the solubility of the coprecipitate phase, in this case, iron phases, magamite, magnetite. So those give you the lowest predicted solubilities in the table. But in general, the performance assessments tended to use the higher solubility predictions. Similar table for technetium, iodine, and neptunium. Won't go through all the details, but similar approach as in the three types of samples they looked at. One thing I'll point out is that for iodine, in general, they assumed no limit for iodine solubility. They assumed that it would dissolve. But in the table, you'll also see solubilities for suspected iodine phases, silver iodide, and mercury iodide. And that will be relevant in a minute. Conclusion. So I didn't really go through a detailed comparison of what we saw versus the predictions. But in general, where is it? Tank 18 uranium leachate concentrations were high and significantly exceeded predictions. Uranium was more soluble, as I mentioned, for tank 18 because of that phase change and reaction with CO2. So uranium for tank 18 and in one case for tank 12 as well exceeded predictions. It turns out uranium is not one of the biggest dose drivers, but they're evaluating all this now with regard to how it impacts their performance assessments. But the other radionuclide concentrations were between predictions for coprecipitated phases and assumed pure phases. In other words, they were below the maximum PA predictions. So in general, the results were good and should have a positive impact on the performance assessments. Other conclusions, we completed the leaching studies. They're really kind of the first of their kind. We observed low metal concentrations, sometimes very near analytical detection limits or even below. Uranium was the most soluble. The iodine solubility was much lower than assumed in the PA. I told you they really acted like it had no solubility limits. It was infinitely soluble. But actually, we observed solubilities in the range of silver iodide and mercury iodide, which were quite low. And really, I couldn't measure them for most samples. So path forward. Kent may try to develop more reasonable targets for pH and EH, doing some simulant testing, because clearly the targets that we've got now are not achievable. We've seen that in multiple tests. And then we may eventually do additional radionuclide release testing, looking at tanks typical of F area sludge residuals. Tank 18 was from F area, but was not typical. So we really haven't looked at a typical F area sludge. H area sludge residuals, we've only looked at the chemically cleaned. And some tanks were not chemically cleaned. So that may be some additional testing that we do. Kent Rosenberger, I'm sure you probably also know Mark Layton, really directed and funded the testing. And a number of people worked on it over a series of years to get us to the point where we're getting actual data from tank waste residual samples. Any questions?
Thank you, Bill. questions for Bill from the audience? Andy first.
Yeah, this question is about the PU solubilities that you reported. I think you were showing about 3 by 10 to the minus 11, even with large changes in EH. And the reason I'm asking is that what we've seen is there's a transition between, we're dealing with PU3 and PU4, and you see a big difference in solubility as, for example, PU3 when we get a slightly higher EH. And I'm kind of curious about your similarity in values, even though your EH values are quite large. Quite different, rather.
Yeah, it is what it is, really. I mean, that's why we do this testing. We don't know. I mean, we have predictions based on the oxidation reduction potential, but until we do it, we don't know what the solubilities are. Now, we did, I gave you predictions. The predictions were based on the targets, and we didn't achieve those targets for EH, which is what's going to potentially change that solubility, that oxidation state, and that solubility. So it depends on what EHs you can reach, which ones are realistic and achievable, and the waste is the waste. It will behave as it chooses to behave. I mean, we don't necessarily know what the phases are. We don't know what the oxidation states are. So.
The water that you were using was, the leachate, was saturated with calcium carbonate, is that right? So do you think you had any precipitation of calcite during your experiment in there?
There was no indication of it.
Okay. Because that could impact some of the iodine, especially, results.
Yeah, it could. It could.
So, yeah, but you didn't see any?
No. I mean, we think this is a representative. We think, calcium. We think that phase is a dominant phase that's present in the system.
Mm-hmm. Oh, yeah.
So if that occurs,
yeah, right. It would be
it occurs, right?
Of an instinct.
But there was no indication that was happening, but it easily could have.
Okay.
Ken, do you want to add something?
I was just going to add to the previous comment is one thing we've certainly learned in all this is that people that are used to plutonium in, I'll say, a waste or at different facilities, with our tanks, some of them have been mechanically cleaned, which means we actually put probably millions of gallons of water in mechanical agitation. So the plutonium that may be representative, say, from production facilities that may have ended up in a solid waste form or something, should not look anything like these solids. In some of the tanks, as Bill mentioned, we did oxalate. Number one, did that mechanical millions of gallons of water in high motion on the sludge to get them suspended and moved. Then we also did oxalic acid, heated oxalic acid cleaning, which again will change the form of the plutonium and what's left. And so that's the one thing we've learned is you got to be very careful when we get expert elicitation on plutonium, et cetera, is, okay, well, I'm used to stuff that comes right out of the production facilities. And that is not what this stuff in the tanks look like, which is why, which makes it more interesting because then we've got to go, and it's, incumbent on us to make sure we have enough data for different types of waste cleaning and et cetera to be able to feel confident that we have enough data to stop doing this in-depth testing because it takes time and it takes money to do some of this testing, but we got to get there.
Yeah, well, you are here. So can you also elaborate a little more about what you may want to do with the set of data? You have tons of data here. Are you going to do some kind of comparable modeling to understand the processes? It sounds like there are a couple phenomena that was not, well understood yet.
Right. I mean, so part of our PA process, you've heard this before in previous talks, is when we get new data, required to evaluate it. So we've done, when we completed the testing on tank 18, we did unreviewed waste management question evaluations. So we redid modeling with the new solubility information compared to what was in the PA. And right now I'm in the process, because he just issued his report a month or so ago. We're actually in the process of making new gold sim runs with the new data and see how that influences the peak doses and timing, and then run through a UWMQE. So yeah, we're rerunning everything and evaluating it. Very similar to what we would do with what Greg talked about with the GSA database. Again, big new information. So we're incorporating that within the Saltstone PA revision because it's in process right now. But we'll also have to go back and do that for the 2 tank farms to make sure there's not an issue there. So just part of our normal process.
In addition to testing the impact on the PA results, what I'm actually was asking or curious to know is whether there is any plan to analyze the test itself to understand the test condition, why you couldn't get the EH as high as you originally wanted, that sort of thing. Yeah.
Well, what Bill said is that the EH and pH states that we looked at were based on, at the time we started our tank farm PAs, based on assumed, stages. And again, that was all literature and et cetera data. And so we were trying to still hit the same targets that were the original analytical. And so that's why one of the first things on the future work is it's obvious that the systems we don't believe they're driving to the extremes that we thought they could. Which isn't necessarily a bad thing to not be at the extremes. That's where we modeled it, but that's not where the systems seem to be going. So to me, one of the first things we should do before we do more waste release testing is go out and take some of the actual grout we use to close the tanks, do some column experiments, run water through it, see what the pH and EH states actually are based on the actual grout formulations we're running with the water the groundwater simulants that we believe will go through it, come up with new set of targets, and then do the analyses to that. Now, if we don't if we don't hit those targets, then we should be scratching our head. But we should, I think that the main thing to do next, because we're not ready to do more testing right now, the next tank that we want to do that's a non-acid clean tank is not to the closure state yet, so we got a little bit of time. So do some cold chemistry work and come up with new targets, and then test to those, because hopefully they're about the same targets that we achieved in this sampling, so we have that data already.
Very good. Thank you. Thank you both. Yes.